Hey, so we are looking at some buffers and how we can start to figure out what's going to happen to our buffer as we start adding different acids and bases to it. So we know we can use ice tables and we could plug in that common ion and see how that affects our final equilibrium. But turns out we got a faster way. Don't you hate that? When the teacher's like, oh, you know that thing you've been doing? There's a shortcut. Yeah, it's one of those. Sorry, guys. We call it the Henderson Hasselbach equation. And some of you have actually already spotted this on the equation sheet, the AP equation sheet. But turns out there is a way that we can take our equilibrium statement, our generic equilibrium, and its Ka expression, and rearrange it to get something that's a little more helpful for us, something that's a little more user friendly. But we do have to do a little manipulation because the way we usually measure buffers and measure acidic solutions is with the pH. We got pH probes, we got pH paper, we got lots of ways we can measure pH. So oftentimes it's the pH that we're testing for or looking at the difference in when we're looking at these buffer systems. And so pH, we know, is the negative log of the hydronium concentration. And so we got to get this by itself. So the first thing we do is we kind of manipulate that H3O plus. And if we're looking at what just happened here, what we've done is we've essentially multiplied by the reciprocal, right? We have multiplied the HA up and we've divided the A minus over, and then we've just flipped it to get kind of that H3O plus by itself. And so we've kind of rearranged. Here we've got, if we want to get the H3O plus by itself, here is mathematically how we would do that. Again, this is if we were using all of our ice tables. And we know we can then take and start to do a little math because we know the pH is the negative log of the hydronium concentration. But if you're going to negative log one side, got to negative log the other side. Well, what's negative log of the Ka? You know that. Negative log Ka is the pKa. And so we end up, when we put that negative log through, we distribute that through, we get negative log of the H3O plus equals the negative log of the Ka minus the log of the HA over the A minus. This is your acid, weak acid concentration. This is your conjugate base concentration. Well, negative log of the H3O plus, that's just pH. Negative log of the Ka is the pKa, which we know is a number we can easily find from any textbook. And then we actually use a logarithm identity here real quick, just to get this a little more user-friendly. The reason this sign changes is we flipped the parts of our division here. So our conjugate base ends up on top, our conjugate or our weak acid ends up on bottom because we flipped that kind of a fraction. The sign on our log changes. That's just a logarithm identity. And so we end up with this really useful kind of shortcut, if you will. So now we have a way that we can actually just straight solve for what's the pH instead of going all the way through the ice table, getting the hydronium concentration, taking the negative log of that, finally get the pH. Nope, we can get it all in one go if we have all of the pieces that we need. And so when we're looking at buffers, we can actually start to calculate what's going on using this equation. And all it does is plops us out pH, which is pretty handy. Cool. And so if we were looking at an example problem here, I'm going to step through this. I'm going to step through at least the first two just to get you thinking, and then maybe we'll do C when we get back together. And so we've got a buffer, right? We've got a buffer, which is acetic acid and some sodium acetate. Again, we don't really care about the sodium. Sodium just kind of floats away, right? And so what remains, the particle we're interested in is that acetate ion, right? CH3COO, that's C2H3O2 1 minus. So this and this first part actually create our buffer. And so if we were thinking about our kind of Henderson Hasselbach equation here, we actually don't have to do much here. We know the Ka is 1.8 times 10 to the negative fifth. Our base, our conjugate base for this is our 0.50 molar. The acid concentration is 0.5 molar. Wait a minute. 0.5, 0.5. These are equal. Log of 1 is 0. And so when we plug this all in, right, pK is the negative log of the Ka. That just came from here. We got 0.5 molar over 0.5 molar. We end up with the pH equaling the pKa. That's a thing we knew already. And that's going to give us a pH of 4.74. And so instead of sending a whole ice table, we actually can go right to the pH using the Henderson Hasselbach. It's really nice, and you'll always have this equation handy. Cool. So if you're thinking about part B, right, in part B, we have a slight change, right? So in part B, we're adding some sodium hydroxide. Now, if we were just thinking about what's going to happen to our pH, don't overthink it, right? Our buffer starts at 4.74. We're adding a base. pH should go up, right? We've added a base. It's going to become more basic. And so now we just need some way to show that or calculate that. We can do a whole ice table, but I don't think we need to, because what is this sodium hydroxide going to react with? Well, it's going to react with the acid. Oh, but this is molarity. This is moles over liters. Oh, well, moles over 1 liter is just molarity, right? So this is the molarity of the base we're adding, right? That's going to use up just a little bit of acid and turn it into a little bit of the conjugate. And so what ends up happening here is our acid is going to go down by 0.02 molar, and our conjugate base is going to go up by 0.02 molar, right? Because we know when we solve for a molarity of our base, we end up with this molarity. If this is our equation, right? If this is our equation, we add 0.5 of this and 0.5 of this. Well, our acid's going to get used up. It's going to react with that base. But whenever it reacts with that base, it's going to make more of that acetate ion. So we're going to end up making more of this, right? We're going to shift it to the right in terms of our equilibrium, right? And so what we end up doing is we just got to alter our molarities a little bit. We add 0.02 to the conjugate. We subtract 0.02 from the acid, plug it back into our Henderson Hasselbach, and we get 4.77, up just a little bit from what we saw before. Well, okay. Given that, we should be able to predict what's going to happen on this next one, right? Part C. Part C, if we've added an acid, well, that's going to react with the conjugate, making less conjugate, more weak acid. And so we actually just reverse what we saw in part B. We add 0.02. We add 0.02 to the acid, and we remove 0.02 from the conjugate base. We can plug it all in, solve for our final answer, which we would expect to be more acidic or lower on the pH scale, because we've added an acid and our pH should go down. Not a lot, but enough that we can measure. Cool. And so this Henderson Hasselbach, armed with this, we should be able to navigate a couple more problems on 19.1 when I see you again.